Okay, any questions? Okay, let's move on. This is an example we can skip. So now that we know about consistency, we can talk about more refined properties. And so this is basically the second important limit law in probability. So the first was the law of large numbers, and this usually leads to consistency results, right? So we built our consistency results on basically uniform versions of the law of large numbers. So weak law of large number again says that if you have a sequence IID, let's say there is a mean and there is a covariance, so the moments are first and the second moment exist, then the sample mean converges to the population mean. That's the weak law of large numbers in probability. So this says that x bar n is consistent for mu. So if you want to translate weak law of large number to statistics, that means the sample mean is consistent for mu. CLT says something about the fluctuations or how big the deviation from the mean is. Now, if I look at the difference of x bar n minus mu, this difference is going to 0. But if I properly scale it, and the proper scale turns out to be root n, then this fluctuation stabilizes. It doesn't converge to anything in probability, but the distribution sort of converges to something. And so there's this CLT, central law limit theorem, is statement about convergence and distribution. So the distribution of these sort of converge to a normal with mean 0 and covariance matrix sigma. So this is convergence and distribution. Again, another mode of convergence that hopefully you guys have seen in previous courses. It's weaker than convergence and probability. It just says that it's the distribution of this guy is getting closer to the distribution of normal random variable. So characterizes the fluctuations. So this turns out to lead to the things that people call asymptotic normality results in the statistics. So you'd show that many of these consistent estimators, like classical estimators, when you look at the deviations properly normalized, the deviations become asymptotically normal. And then you can use this covariance matrix sigma, in the univariate case, the sigma, as a measure of the uncertainty, asymptotic uncertainty of your estimate. Instead of trying to compute the variance of the estimator, which is usually difficult, you have this nice result, and then for sufficiently large sample size, you can approximate the variance of root n x bar n minus mu. So you could say basically, this is not correct, but you can say that roughly the variance root n x bar n minus mu is roughly let's say this is sigma square, like that. Okay, so you could say basically that, I mean, I can move to the other side. X bar n minus mu is roughly sigma squared over n, which you already know that this is actually exactly true for the sample mean, but later on, so you'd say, for example, x bar n minus mu is with high probability. Let's say this is going to be bounded by some constant times sigma over root n. So if I go a distance, so this is the variance. So if I go a constant factor away from the mean, scaled by this variance, then I would have most of the probability. So this holds a high probability. So in other words, x bar n is roughly, this is approximate everything, approximately mu plus minus, let's say, O of sigma root n. I'm going to put a p here because we'll see what p means here. But basically, it's mu plus minus fluctuations that are order 1 over root n. So you already know this for the sample mean because the variance is exactly the other side. But later on, we're going to prove, based on the CLT, you prove, for example, that the MLE has this property. So root n minus this time, and minus the actual parameter that you're trying to estimate. This also converges in distribution under regularity conditions. Actually, it goes to a variance, which is going to be the inverse of the Fisher information. And so this gives you a similar behavior. So the MLE is theta naught plus minus, so data hat n would be, so this is the MLE, would be theta naught plus big OP of 1 over root n I theta. So this tells you how big of a fluctuation you would have. Again, the scale is 1 over root n. And the more, the larger this Fisher information is, the smaller the variance, asymptotic variance. So these are called asymptotic variances, asymptotic covariance. It's not the same as the variance of the estimator, but if you have a law like this or a converter like this, then you just call the asymptotic variance. And you'd also say that the estimator is asymptotically unbiased for theta naught. It doesn't mean that the expectation converges to theta naught. It's a terminology. Neither the variance is converging to the variance of the normal, nor the mean converges to, but this implies that is unbiased for the asymptotically unbiased. That's the mean, like the terminology for theta naught. What it means, it just means what I wrote here, right? So intuitively, it's like approximately zero mean, so approximately unbiased, but precisely it just means what I wrote here. So is the idea clear? So that's what we hope. So we're going to translate this CLT to statements like this for the MLE or other estimators, other M estimators. You can do it for a lot of classical estimators. So have people seen CLT before? Okay, how about this, like this statement about the MLE? Some, okay, a couple of people have seen it. Yeah, so we're gonna do that shortly. Any questions? Online people, questions? You still can hear me, right? The online people? Okay. No questions. Okay, so in order to do that, let's try to review some facts about the relation of these convergence. Basically, we want to develop some calculus, how to manipulate these convergence statements without going back to the definition every time. So let me ask you, just formal definition, what does this convergence distribution mean? If anyone remembers? Yeah.
It's the empirical distribution sequence converges bias to the asymptotic CDF.
Okay, great. So yeah, the technical definition is sort of what you expect, except some sort of technical caveat. So let's say the sequence xn converges in distribution to a sequence x, sorry, to a random variable x. This is a sequence of random variables. This is another random variable. You write it like this, but the statement is really about distributions. There's nothing about random variables actually like existing. They don't even need to exist on the same space. I can write, for example, xn convergence distribution to normal 0, 1. This is also valid because the statement is about that. So if this is like univariate, so 1D, I can look at the, so Fn, let Fn be the CDF of xn, basically probability that xn is less than or equal to t, that would be Fnt. And let F be the CDF of x. Basically this statement. Then what can I claim? I can claim that, so this is basically equivalent to, like that's defined basically, defined as this converging to f for every t for which f is continuous at, let's say. So at every point that f is continuous, so the limit is continuous, or the set of continuity points of the limit, I should have the convergence as n goes to infinity. So it's about the convergence of a pointwise convergence of the CDF, basically, at points of the continuity of the limit. And the technical part is this. So if the limit is continuous, let's say it's a normal random variable, the CDF is continuous, I have to have the convergence at every point. This is usually what we care about. There is a more general version of this definition. So this is hard to extend to, you can still extend it to, let's say, vectors, because you can define a joint CDF, but then continuity becomes a little bit messy. But let's say I have more exotic objects. I want to define convergent distributions. Is there another alternative definition that is more easily generalized? Anyone is seen? How else can I measure like convergence in distribution? Any online people know about that? Yeah. Sorry? Yeah, great. So I'll pick some test function. So alternative definition. Pick some f, like f, which is a test function, apply it to this sequence, and then take the expectation. This is a number. And I'm going to require that this converges to expectation f of x. If this holds for f in some large class of functions, for example, continuous and bounded is good enough, then I would say I have convergence in this distribution. This is a very general idea in mathematics. If you want to study like objects, you can define functionals on the objects and study the functional. So instead of working with the distribution, this is like a functional. So the function that the mathematical object that maps f's to these numbers, this is called the functionals because it takes functions, it outputs numbers. And this functional characterizes a distribution of xn, basically. So instead of looking at the distribution, you can see what are the expectations of functions of this random variable. Basically integrals against the measure, which is the distribution of xn. And if sufficiently many of these, for sufficiently many of these f, I have this convergence, then the distributions have to be close. And the technical idea is that if I require it for continuous and bounded, this would be enough. It would be equivalent to the previous definition, but this is generalizable. I can generalize it to vectors because I know how to define continuous bounded functions and vectors. It could be like xn could be a measure, a matrix, like a graph, whatever. As long as I can define some sort of topology, makes sense to continuous functions, then I can define convergence distribution. Actually, I can define distribution. So you can say two random variables have the same distribution if the two stack expectation of, what I mean by, so if the expectation of f of x is equal to the expectation of f of y, for any collection of these functions, I'd say they have the same distribution. It's a very interesting idea. Just point that out. So this you can see is clean, and then I can restrict the. So for example, what this definition is saying is that restrict the class f to the class of all functions that are indicators. So all the things that look like indicator in the univariate case, where t is in R, and t like belongs to the continuity points of f. This is like script f. So if I restrict myself to this class in the univariate case, it's good enough. In general, for example, you can restrict yourself to again, in the univariate case, to these functions that are like t dot, so like the exponential functions for various values of t. This would give you the characteristic functions. So you'd say expectation of t. Actually, so let's say I. There's like the these are bounded because of the I is like the imaginary sort of number. This would be equivalent to convergence of the characteristic functions. So these are continuous and bounded, so it's a subclass of this, but you can show that if you have it for this subclass, then you'd have it for all continuous and bounded functions. So that like it is a theorem that convergence of characteristic functions is equivalent to convergence of convergence distribution, but that's just like a mathematical fact. If something holds over these are like sines and cosines, basically. If you can sort of reconstruct sines and cosines, then you can reconstruct any continuous bounded functions, like a Fourier sort of idea. Okay, so this just point out that this is a very nice definition. And from this definition, some of the properties of convergence distribution more immediately follow. For example, if I have xn converge in distribution to x, then any continuous functions, let's say g of xn, converge in distribution to g of x if g is continuous. Okay, so this immediately follows from this definition, because if I compose a continuous function with another continuous function, then the result is continuous and it also remains bounded. So f of g would be bounded. So this results, for example, follows from that. Enough to take f to be this, or in the 1D case, enough to have this, and so on. Okay, any questions? This is like a short review. Doesn't do the convergence distribution justice, but this idea I think is very important. So questions? Okay, so then you can go and prove things. So you can go and prove that these results hold. I'm not going to prove it. You can look at some of the references. For example, asymptotic statistics book has a lot of these ideas in the first chapter, I believe. So convergence probability implies convergence distribution. That's the first property. So if you really have a sequence of random variables that converges in probability, then the distributions also converge. The reverse is not true. So this means that the convergence distribution is weaker. If you have convergence to a constant, however, then the reverse also holds. So convergence to a constant doesn't matter if you put P or D, so they're equivalent. So that's this part. We have the continuous mapping theorem that if you have xn converges to x and f is continuous, then f of xn converges to f of x. This holds for convergence distribution and convergence probability. So I mentioned the proof for convergence distribution using this simple characterization. For convergence probability, you can also prove it yourself as an exercise. It's simple. So we'll refer to this as the continuous mapping theorem. So if you have convergence of, actually it also holds for the almost sure convergence, obviously. So any form of convergence, these three types of convergence, then you apply continuous functions, things would hold. There's this Slatsky's lemma, which is really important to us. So xn converges in distribution to x, yn converges in distribution to c, a constant, then the pair, so this is a random vector, it can converge in distribution to the distribution of another random vector, and it turns out that it converges to the distribution of x and c. This is like a singular distribution in R2, let's say if they're univariate, but that's the nature. It has a distribution and you converge to that. This lemma does not hold if this other side, if both of them are random variables. So one of them has to be converging to a constant. You can't have both converge to genuine random variables. The result doesn't follow. unless I guess you have independence, but this is not assuming any independence. So this is any sequence, there's no assumption of joint distribution. We don't know about the joint distributions. Of course, you can replace this with P, because convergence to a constant. For a convergence to a constant, D and P, they're equivalent, but it matters that one of them be converging in distribution to C, like a constant. However, for the convergence probability, you have the result that if this converges to in probability to X, this converges in probability to Y, then the pair converges to the distribution of the pair. This is another instance of the strength of convergence probability. So convergence probability is strong. The other thing is that if Xn converges in distribution to X, and you have another sequence such that the difference of that sequence to your original sequence, so Yn and Xn, the distance is going to 0 in probability, then Yn also converges in distribution to X. This is also very intuitive. This is like saying, in univariate case, Xn minus Yn goes to 0 in probability. And so one of them converges in distribution to something, the other has to converge in distribution to that. So these are the basic properties, and basically we can use this to do a lot of work. For part C, the continuity of F only is required on the set C on which X puts its mass. So if I have a set C such that the probability that X belongs to C is 1, I only need F to be continuous there, as you can imagine, because like in probability, most of the things that we talk about are still true if hold on a set of measure 1. And this is indeed the case. And D, as I mentioned, does not hold if C is replaced by some random variable. Questions? I'm going to give an example of that, the failure of D in that case, shortly. So the thing that I wrote as a Slutsky's lemma sometimes is not stated like this. Instead, the consequences are called the Slutsky's lemma. So consequence says if you combine D and C, you can get very interesting consequences. So for example, if I have Xn converges to D, in D to X, and Yn converges in probability, in D, let's say, to C, I can define the function f of x, y to be x plus y. This is a continuous function. Because of this Slutsky, I know that Xn, Yn converges in distribution to X and C, and then I use the continuous mapping theorem to apply f to this. It's a bivariate continuous function, so this has to converge to this, which is equivalent to saying that Xn plus Yn converges in distribution to Xn plus C. So that's usually what is called conversion of Slutsky's lemma. So the Xn converges to X, Yn converges to C in distribution, and Xn plus Yn converges to X plus C. You can apply any continuous function. For example, you can say Xn times Yn converges to C times X. Or Yn inverse Xn converges to C inverse X. For this, you have to worry a little bit about. So X over Y is, so this function is continuous except where Y is 0. So if I require that C be non-zero, then this function would be everywhere continuous where the mass is there. Like this X and C puts all the mass over the area in which this is continuous, if C is non-zero. And in fact, the way I wrote this is from the asymptotic statistics book. So you can think of Xn, Yn being a matrix, Xn being a matrix. This is a matrix, another matrix. So as long as C is invertible as a matrix, then this function is like continuous at the limit, or at this, let's say, the support of the distribution of the limit. And so this holds. So you can do these easy manipulations. So this is what you would like to do. So if I have X and Y and I want to replace, let's say, Yn with the constant, the limit, and you can just do this. So this allows you to replace, let's say, xn plus yn, replace yn with c, that's the limit basically. So this is what you would do in a calculus course. So this is telling you that these are valid for convergence in distribution. Questions? How many people have seen the Slutsky's lemma? 1, 2, okay. Yeah, so this is really for a probability course or a course in asymptotic statistics that is dedicated to asymptotic statistics. But I'm not going to prove it. Most of them you can prove for yourself. Some of them are a little bit more tricky. The proofs are not difficult though. So the notation that I'm going to introduce here is going to be helpful. So if something converges in probability to 0, we write it at x, the sequence is little op of 1. So if you're familiar with the O notation from analysis, little o means converges to 0. And here little op means converges to 0 in probability. Okay. Then these rules that we develop, they tell you something about doing calculus with this O notation. So for example, if I have an OP of 1 term and I add it to an OP of 1 term, then I get an OP of 1 term. This is basically using this fact. So let's say xn converges in probability to 0, yn converges in probability to 0. These are also in distribution, right? So then xn plus yn converges in probability to 0. Okay, so that's the translation of this. Xn is OP of 1, yn is OP of 1, xn plus yn is OP of 1. So these mnemonic rules you can use. Once you get comfortable, basically, you can use this to simplify things without necessarily writing formal limits. So this equivalent to that. Defined like this. Questions? So here's a simple example of this. So xn convergent distribution to z, which has a standard normal distribution. I can apply the continuous mapping theorem. So the function f of x equal x squared, this is continuous everywhere. So then xn squared converges to z squared, and z squared has a chi-squared with 1 degree of freedom. That's the distribution. So xn squared converges to a chi-squared randomly. So the next is the counterexample. Suppose xn is a sequence whose every element is x. So it's a constant in the sense that all of them are the same random variable. Xn is equal to x for all n. And x happens to have a uniform distribution. Okay, so basically it's sequence x, 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 dot, dot, dot. I have another sequence yn that's equal to xn if n is odd, and 1 minus xn if n is even. So yn would be like x, 1 minus x, x, 1 minus x, and so on. It just flips between x and 1 minus x. So xn convergence distribution to x, it should be obvious. Okay. Yn also convergence distribution to x. Why? So obvious. It does. Yeah. Sorry, say that again. Yes, okay, great. Yeah, so 1 minus x basically has the same distribution as x. It's uniform 0, 1. And so every element of the sequence basically has uniform 0, 1. that a sequence that has like constant distribution obviously converges in distribution. So we have these, but the idea is that the pair x and yn does not converge. Easier to do this. Okay, it doesn't converge. Online people, can you hear me? Yeah, is it good? Hello? Yeah, okay, good. So x and yn does not converge in distribution. It actually doesn't converge to anything in distribution. Any idea why? Yeah.
We could use our like expectation definition. The sum's gonna be like bouncing that. If it's, I forget if it's odd or even, but like when it's even, 1 minus xn plus xn.
One minus xn. One, let's say one once would be like, okay, so xn is always x, right? So this is always x. This is sometimes x, sometimes 1 minus x, right? So you're saying the sum would be either 2x or 1, right? And
So if you use your expectation definition.
okay. Expectation of what though? Like the thing is, this is not a bounded function, right? It's fine, but so you're going to say this doesn't converge to okay, so this has to converge to something. So you're saying this is not converging. You have to like let's say if I want to define a proper function, let's say I define a function which is okay, good. Yeah, so we'll do this. So x plus 1 if let's say x plus 1 is in 0 to 2. Right. This is a bounded function, continuous. It's actually not continuous because it drops to 0. But if you define it continuously, let's say x plus 1 0 if x plus 1 is less than equal to 0. X plus 1 in 0 to 2 basically, and then 2 if x plus 1 is bigger than 2. Something like that would be continuous and bounded. And because this is going to be in 0 to 1, 0 to 2, and this is in 0 to 2, it's as if we're applying it just to this part. And so it's easy to see that this is going to be like expectation of 2x and expectation of 1 for even or odd sequences. And these are going to be different. So the expectation of this would be, so actually this is equal. Okay. Did not work. But the idea is there. Okay, so you may be able to manipulate the function a little bit to
We actually change the truncation region or whatever.
we could do that. Yeah. So I encourage you to try this. This is an interesting argument. An easier way to see like more generally without worrying about. But this is a good way. So you can apply find a test function for which this expectation. The claim here is that actually doesn't converge to anything. The easier way to see is that if you look at the distribution of the sequence, so what does the distribution look like? So this is going to alternate between will be equal to like xx versus x and 1 minus x. Okay, so the distribution of xx is if I want to plot it in this like x, like this is xy plane, what would it look like in terms of the point clouds, let's say? a random variable whose coordinates are x and x, where x is uniform. Yeah, it would be like uniformly distributed on this 45-degree line. How about the other one? X and 1 minus x. Yeah, the other one would be like uniformly distributed on this. Right? Because they sum to 1, so it has to be this. So the distribution of this sequence alternates between these two distributions. So it can't converge to anything. Okay. I guess you pick the right, like at this point, they're going to be equal, sort of. I don't know. So this function sort of symmetric, but you can manipulate the function to be able to like pick up. Maybe if you hit this point, you can see that the values are different, something like that. Okay, great. So this tells you why things would fail. So you have to be careful about the Slutsky. Questions? Online people? Okay, here's another example. So we have an IID sequence. The expectation is mu, variance is sigma squared. I look at the sample mean, and this is the sample variance, one version of the sample variance. And you can write this as, this is basically the variance of the empirical distribution, if you think about it. You recall the empirical distribution was this measure. This is a probability measure, has everything like mean. The mean of it is just the sample mean. The variance of it is exactly this. And because it's a probability measure, it just has the same properties. Like this is like saying, sometimes people write this like, you'd see some people write this as Pn applied to x minus Pnx squared. This is like expectation if you want. And this is like Pn applied to x squared minus Pnx squared. Think of Pn as applied to a random variable as taking expectation under. So Pnx just means expectation of x, assuming that x is distributed like Pn. So you can see Pn is a measure, it just has the properties. The expectation with respect to it has all the properties. So this is like the formula for the variance, basically. The two different formulas for the variance. In any case, so this is Sn. So now I'm gonna form this statistic, which is T. This is called, if you've taken like any basic statistics course, you know about t-test, things like this, right? So the T statistic would be Xn minus mu. Actually, this is not the statistic, but this is how you get to the statistic. So you want to say test whether mu is 0. This is what you do. So Xn minus mu divided by root Sn basically squared. Actually, this is, I need to do like root Sn squared divided by n. So this is an like estimate of the, so the variance of n is sigma squared over n. So this is like estimate is Sn squared over n. And so if I remove the mean and divide by the estimated, this is the standard deviation basically of x bar n. Estimate the standard deviation. We want to say what happened, like we want to see what happens to the distribution of this guy as d goes to infinity. Sorry, n goes to infinity. So if I had x bar n minus mu divided by sigma squared over root n, things would have been simpler. But in fact, it doesn't matter, as we'll see. So I can use the things that we described, or the properties that we derived, to find the limit of this. Okay. So for example, I know that x bar n converges in probability to mu. Okay, so for example, I can say that x bar n minus mu converges in probability to 0. What can I say about Sn squared? That's the this guy. Can I say that it converges to something? Let's say this is 1 over n summation I from 1 to n. This minus 1 over n summation, basically minus x bar n squared. Does this converge to anything? Does this converge to anything? Converges in probability by the weak law of large numbers to what? To expectation of one of them squared, right? This is the second moment. This would be basically sigma squared plus mu squared, right? Then you can use the Slutsky. So this is a sequence that converges minus, basically apply. So I know that x bar n converges to mu in probability. I'm going to call this x2 bar, okay? And so x2 bar n converges to sigma squared plus mu squared. Then I apply like this Slutsky type argument to this function, like x minus y squared. Right, this is a continuous function applied, so I get that x bar applied to the second one, like this minus x bar n squared converges to sigma squared plus mu squared minus mu squared, which is just sigma squared. So this converges in distribution because both sides are constants. Convergence in probability and distribution doesn't matter. So an application of weak law of large numbers plus the version of the Slutsky tells me that this converges to sigma squared in probability or distribution. Okay, so that's the tricky part. Then so what I have is, so these are some basic things. Also, I can do the ideal version. So x bar n minus mu divided by sigma squared over n, right? This is like root n x bar n minus mu divided by sigma. This by CLT converges in distribution to normal 0, 1. This is classical CLT you can verify. It's just normalizing by subtracting the mean, dividing by the variance, basically, or the standard deviation gives me IID sequences with 0 mean and varying 1. So now can I combine? So if you look at this and this, the only difference is what? Is replacing sigma squared with Sn squared. So what I can do is that I can write x bar n minus mu divided by root Sn squared divided by n as, let's say, root sigma squared divided by Sn squared, and then times x bar n minus mu, and then root Sn squared divided by. So divide and multiply by sigma squared divided by Sn squared square root. Okay, now this is sigma squared. So this is hopefully true, right? So this converges in distribution by the CLT to normal 0, 1. We know this is true. Can I conclude that Sn squared divided by sigma squared converges, let's say, in distribution to 1? Is this true? Yes, it is true because of the Slutsky, and I can do all these manipulations. So this is, and then the square root, of course, also continuous mapping theorem. Slutsky plus continuous mapping theorem gives you a lot. And then also, in fact, the other way around, and I can like flip things, that's another continuous function because their limit is like non-zero. This is actually true, right? Does this make sense to people? We can like do all the steps, right? So divide this by sigma squared, take the square root, and then flip. All of them are continuous functions. So this basically is converging in distribution to 1. So I have a sequence that converges in distribution to 1, another one which converges in distribution to like a proper distribution. So the result converges in distribution to 1 times normal 0, 1. Right, that's the Slutsky and the proper usage. So one of them converges to a constant, the other to a proper distribution. So it's like xn convergence distribution. Let's say zn convergence distribution to 1, yn convergence distribution to normal 0, 1. Then Slutsky tell me zn yn convergence distribution to 1 times normal 0, 1, which is again, of course, normal 0, 1. Okay. So all this work, which is not difficult, just application of these, tells me that this is a statistic that I define, a t. This is converging to a normal random variable. So in classical like statistics, if you divide by let's say if this was 1 over n minus 1 and things were Gaussian, this would be a t this t distribution under the Gaussian assumption. Hence the t-test. However, this is like an asymptotic result, doesn't assume any normality, and the t actually asymptotically converges to a normal. Okay, so this is called sometimes a distribution-free result. So you didn't assume any distribution for your data, but your statistic has some sort of a well-behaved asymptotic distribution. I can use this to test, for example, whether mu is 0 or not. So if you have seen how to build confidence intervals or do tests, basically you can, we'll talk about this later, but let's say say if I want to do a hypothesis test, talk about these later. I know that under the null, under H naught, basically x bar and mu is 0, right? So I set mu to 0 times root ns, basically this guy. This is well defined from my data, so this converges to normal 0, 1. So if I reject the null, so reject H naught if x bar n divided by root Sn squared. This is bigger than some tau. I can set tau using the normal quantile such that asymptotically I have a certain level. So we'll talk about this if you haven't seen hypothesis testing. Don't worry about it. But one advantage of these results is that you can use them to build confidence intervals or tests that are asymptotically valid. So that's the main use, traditionally in statistics at least. Okay, because we started a little late, maybe just a few words. This is clear to people? Okay. One last thing, maybe just a few more minutes. So there's another topic, like there's another concept. So we have convergence probability, convergence distribution. There's another notion which is equivalent to boundedness in analysis. So we have a little OP of 1. There's a big OP of 1 as well. Big O means something is bounded, as like a sequence might not converge. For example, this sequence that we had, the sequence of distributions that you see xn, yn, this sequence does not converge to anything in distribution, hence not in probability as well, but it's bounded in probability. So the random variables are not like going to infinity. So it's an example of a sequence that does not converge, but it's like bounded in probability. And this is the notion of boundedness in probability, also called uniform tightness. It's like a jargon, probabilistic jargon. So a sequence of random variables is uniformly tight if for every epsilon there exists an m such that basically for all n, probability that xn is bigger than, that the norm is bigger than m is less than epsilon. So I can choose basically M. Uniform here means M works for any N. So it's like you look at the sequence after some point, basically, all of them are going to be less than M with probability epsilon. So pick epsilon, like probability 1 minus epsilon. So basically, for N large enough, basically Xn would be less than or equal to M with probability at least 1 minus epsilon. You can pick epsilon whatever you want. You can find an M, which depends on the epsilon, such that the sequence eventually at some point is like bounded. So you can bound the sequence, like the future of the sequence, at any level of probability that you want. So with probability, if you let me, like, if you want 0.99, I can find a constant such that the probability 0.99, like the sequence is there. So this sort of prevents things to escape to infinity. So you can have sequences such that the mass sort of gets like pushed towards the infinity, and like eventually, like everything is gone. Things are at infinity. So this prevents things from happening. So it's like an interesting technical condition. Intuitively, it's like the boundedness. So for all intents and purposes, it's like boundedness, but a probabilistic version of it. So if you know bounded sequences, this is like the proper way of defining it. If a sequence converges in probability to 0, another sequence is uniformly tight, then the product converges to 0 in probability. This is like saying if a sequence goes to 0 and I have a bounded sequence, the product converges to 0. If a sequence converges in distribution, then the sequence is uniformly tight. This is another important result. Things that converge in distribution cannot go to infinity, like mass doesn't escape, so you're uniformly tight. And so the first statement you can write as, so things that are uniformly tight, we write big OP01. So little OP01 times big OP01 is little OP01. So that's statement A. And combining these, you can do a lot of calculations. So next time, hopefully we're going to use this to prove the next big result, which is asymptotic normality of M estimators. And this slide is not correct, so this is not correct. I'm going to try to upload the correct version. So part B is not correct. But thank you, and see you next time.